Kumar sir.
Sir.
Yeah, I think we can start, sir. Sir is asking, sir is ready.
Okay.
Yeah. Check Mahesh sir. Mahesh sir, are you there?
Mahesh sir will be.
Available, sir. Okay.
Yeah, fine. Kumar sir,
Okay,
start.
okay. So, good morning to all of you participants. STTP on RTHEVT. So, today we have two speakers with us. So, first session will be taken by Professor B.L. Narasimharaju Garu from NIT Warangal. And second session will be in the afternoon at 2 o'clock. We will announce later what is time, that one. And I request our colleague, Mr. Mahesh, to speak out the profile of Narasimharaju Garu. So please, Mahesh sir, can you just introduce Narasimharaju Garu to our participants, please.
Very good morning to one and all, sir. This is Dr. Mahesh Raju from Mechanical Department, MVGR College of Engineering. Today I am here to introduce you our distinguished speaker, Dr. B.L. Narasimharaju Garu, who is presently working as Associate Professor, Department of Electrical Engineering, National Institute of Technology, Warangal. And coming to his qualifications, education, so he did his BE in Electrical and Electronics Engineering, UVCE College, Bangalore, in the year 1999. He pursued his ME degree from Power Electronics in specialization of Power Electronics, UVCE, Bangalore, in the year 2002. He pursued his PhD from IIT Kharagpur in 2011, and the work he did down is like an improved bi-directional converter. That is the topic in which he pursued his PhD. So coming to his various experiences, totally he had 18 years of research and academic experience. So like firstly, he started his career as a project trainee at DRDO Bangalore in the year 2001 and 2. Later, he worked as a teaching assistant at Department of EEE, UVC College, Bangalore in the year 2002 and 2003. Afterwards, he joined as assistant professor at Department of EEE, Manipal University. He worked there around for a duration of 9 years, close to 9 years. Afterwards, he joined as assistant professor at Department of EE at NIT Warangal. And he worked as assistant professor for 6 years. And presently, like he's working as associate professor at Department of EE, NIT Warangal from 2018 onwards. So coming to his research interests, like his research interests are like power electronics, converters, PWM techniques, applications of lightning systems, drives, power quality issues. These are the major areas of research. So coming to publications, he had 21 high impact factor journals published in SCI, SCIE journals, IEEE, IET, IETE, etc. And coming to his international conference proceedings and all, like around 30 different papers he published in various international conference proceedings and 9 national conferences. So coming to his he supervised several students. Under his esteemed guidance, two are pursuing their PhDs and 2 already finished their PhDs. So coming to PGs, like 24 dissertations of 24 PG students he had done. And project assistance he has given for 6 different projects there. So coming to organized elements, like he organized several conferences and workshops all across the globe. So coming to the project status, he has 6 ongoing approved sponsored funded projects to a tenure of 250.35 lakhs. So coming to the awards, he received the best paper award for at IEEE International Conference INDICON 2015 for the paper entitled Modeling and Analysis of Voltage Controlled Positive Output Synchronized Buck Boost Converters. And he received fellowship from MHRD for a doctoral study at IIT Roorkela. and CISR Young Scientist Award for 2010 fellowship he received. So coming to various professional body activities, like he's a senior member at IEEE, life member at ISTE, and life member of System Society of India. So coming to additional responsibilities, he's heading several departmental and institution level other responsibilities additionally, sir. Sir, thank you very much, sir. Thank you for you being here for this particular STTP, sir. Thank you very much.
Thank you, sir. Thank you, Mahesh, sir. Sir, I request Narsimraj Garu to take over the session and present your lecture, sir. Please, sir.
Thank you very much, Dr. Mahesh, for a detailed introduction. So it's my pleasure. Okay, today's talk is basically on this. Of course, I know that the workshop title is on hybrid electric vehicle systems. See, when we say this hybrid electric vehicle systems, power plays a very important role. That's the reason that, okay, so I have this pleasure to discuss something on this power converters and control techniques for power management system in electric vehicles in specific. So that it will fill your, see the theme of your workshop that you are organized. See, as you all know about, of course, most of the speakers have discussed about this, what is electric vehicles and all these things. You might be knowing all these, and because your theme is of this electric vehicle systems. So now, good morning to all participant audience of today's session, and I take this pleasure to put forth my some of the power aspects in electric vehicle systems. So the power converters and control are the backbone of electrical vehicle systems. In electric transportation, without power and its power management, so then we can't say that it's an electric vehicle. That's the thing what we need to understand first. If I say it's electric vehicle, yes. So what is this power? What is this energy? And what is its utility scenario in the power sector? See that here that the brief energy statistics, energy utility statistics. It means that the consumption for various applications today, of course, what we can come across. Roughly, see, we can see this diagram with even the distribution diagram for the various applications. So, of course, this is the latest statistics, and this doesn't show this what is the consumption to vehicle systems, but otherwise the consumption of electric vehicle systems, of course, it is not much significant in presently in India. So that's the reason that, okay, so I have not shown that, so that can be a part of this others classifications. Otherwise, the various applications where we do utilize the energy in cooling system, lighting, office equipment, refrigeration, ventilation, space heating, cooking, water heating, and industrial sector, and so on and so forth. So these are the prime aspects where we need the energy. And now that today is yes, the another important thing is that vehicle system. So we need, when we go for the electric vehicle systems, see, the intention is the simple, of course, as you all know about. See, the what is the need of going for electric vehicles is of to the first and foremost is to cut down the pollution and cut down the noise and to harness the resources, the energy resources which are available in the nature. So this is a prime reason why we do go for electric vehicle systems. So that's what, yes. So therefore, now our power plays a vital role in this vehicle systems. And the future days, yes, we are going to have a most of this transportation system, right from the light vehicles to heavy vehicle, say in terms of electrification, in terms of electrification of the transportation systems. So this is the future goal across the globe, of course, in our country as well for the future. Yes, so this is little something about what is actually, of course, as I understand, I don't know how many participants background from circuits branches. So probably most of the participants, I guess, maybe from mechanical background.
70% mechanical, sir. 30% electrical, sir.
Oh, electrical is also is there?
30% of participants are electrical, sir.
Oh, that's really great. Of course, they do understand better, and of course, no doubt, other people also, of course, they can do understand what is the role of power in the vehicle systems. So that's good. Yes, when it comes to the grid part, the electrical grid part, see, we have now, we say, because of the various energy resources that is available in the nature, see, we can say the grid can be of AC grid or DC grid, and conventionally we call it as a like AC main grid, just simply grid system, that's of AC grid only. Now, because of this distributed energy resources, the distributed energy systems like solar, wind, fuel, okay, biofuel, also different kind of energy resources when it comes into distributed generation system. So we can have a grid of micro level, nano level, okay, as well. Therefore, here what I am showing here, it is that in this particular slide, it is of AC microgrid. AC microgrid, of course, see, we can have this AC microgrid from the distributed generation system. So like PV, wind, all this. So here we can just look at this for a PV and wind could be the assisting energy resource for AC microgrid, and as well the other thing is fuel cell. See, we have this fuel cell, fossil fuel cells, and PV, wind. All these are the energy resources where we can tap and where we can do create a grid. So which maybe with micro level or macro level or okay, mega grid like something. Okay, so that is the thing here. And the other thing is that okay, we can do integrate, we can do means interface the different resources, energy resources to create a grid. That is fine, but having created that grid, then what is the thing that is required here? See, when I say the microgrid, it can be of a standalone grid, or it can be a interface to the main grid. So that's one thing what we can do understand. If I say the main AC grid, whatever this distributed energy resources from which we create a grid has to be integrated into the main grid. That's the thing what we need to do. But at the same time, if it is a standalone grid, so there is no need to integrate into the grid, integrate into the main AC grid, where we see the main power supply, to understand better. Okay. But the thing is, if it is a standalone grid, the utility, what is the utility for the standalone grid? Of course, the loads, any kind of loads, whether it is a domestic, industrial, or outdoor, indoor, whatever, what's not. So anything can be a load, but they are like a feed from the standalone AC grid or DC grid, DC microgrid as well. Okay, I'll discuss that DC grid in the next thing. And if it is a standalone grid, if we do create it, we need to have a grid reference. For that, normally, suppose when the main grid, if there is no, when we are not integrating with the main grid, so then at least we need to have a what is it? The reference, the grid reference, grid kind of reference. So therefore, normally we use a DG sets to give a grid support, a grid reference to the standalone microgrids like something like. Then other part is that, okay, the loads can be connected to the created microgrid, but otherwise, what else is required? See, when we say the resources we are tapped into this grid creation, the storage is another thing which, of course, that is as we understand, the storage means it is a battery storage, energy storage. Okay, basically it is a battery, what we can call it as. Okay. So, but to balance between the storage and the resources, and that means to manage the power from to storage system and storage system back to the load, or directly to the load, or simultaneously to the storage. And if the storage is filled, then only supply to the load. If the loads are also not there, so what should be this? So the maintenance of the grid, that which is created from the various energy resources, is a very, very important thing. So when I say this power management, so that is the thing what we need to understand. So next, yeah, in similar to the AC microgrid, of course, we can also have a DC microgrid. What is a DC microgrid? Of course, we know that AC is nothing but alternating current signal, but DC is like a direct current signal, right? So, but when we say the DC, but in conventionally, as we feed most of the electrical systems from the main AC grid, most of the loads are designed to operate with AC source. So, where in which AC grid supply can be utilized readily. But when we say the DC grid, so it is something like, okay, it is a direct current, but the thing is that now whatever the loads what we do operate with this electric power supply, that is from the AC grid, so it need to be, of course, designed to cope up with a direct DC operation system. That means, so the load elements must be designed to operate with a DC source, not with the AC source. Then only this DC grid is useful. Then only the DC grid is useful. Otherwise, say when we say if I say the induction motor, for example, as most of you people do understand, the induction motor, which is of a AC motor, even in the normal, or what is that in the fans, what we do is a single phase induction motor only. So if you know that AC motor means, okay, it needs a AC signal, but can we operate this AC type induction motor with the DC signal? No, not at all. So if at all if you need to operate that AC motor AC with this DC source or DC grid, then you need again one more converter, that is a DC to AC conversion, which is so-called the inversion or inverter. Okay, that inverter is required to operate the AC drive or AC motor from the DC grid. That is the thing. But in the other side, suppose you need to, if you want to directly take the DC supply to the load element, and then your load has to be operate with the DC. That means your load is supposed to be designed to operate with a DC power supply, not with the AC. Okay, so that need to be taken care of. Of course, there is no doubt now today, nowadays the things, most of the, even right from the see the fans, the refrigerators, or any okay, domestic appliances, so on and so forth. All these are see now coming in the market with see for a DC source fed. What is that? Which can be operated with a DC source. That means these things will be designed to operate with a DC supply, not with the direct AC. But yeah, why we actually, as we already have the load systems of AC, why we need to go for DC means the thing is that okay, the most of the energy resources, what is that? Say for example, fuel cells, photovoltaic, all these things, they are a direct DC signal only. The PV system, PV cell, of course, it gives a DC signal, not the AC signal. And when we get this DC signal directly from the natural resource, energy resource, and just we can create a direct DC grid rather than AC grid. That's the point what we need to understand. So therefore, then if at all we need to put this DC generation into the AC, yes, again we need to use an inverter, and that can be given into the utility grid. So of course that can also be, you can see from the DC microgrid we are giving into the AC utility grid. But for that, the inversion is required. That means one more power conversion stage is required. So that is need to be done. But not only that, when you want to integrate or interface these DC energy systems to the utility grid, there is several issues that need to be taken care. That is another very important thing, because it's not that so easy, because of, there are various issues that which comes into picture. So to interface or integrate into AC utility grid. What is those main challenges? See, when you want to interface these DGs, the DG is nothing but distributed generation, which is utilized from the natural resources like solar PV, fuel cell, etc. So to integrate these DG system to the electric grid system, the main issues what I mentioned, which is like the capacity sizing of the distributed energy resources and energy storage, and maintaining the voltage, frequency, power quality. So these things are very important. The second point, that is maintaining the voltage level of the grid and frequency and quality, power quality. Power quality, when I talk about, say, power quality, here there are several issues like voltage sag, voltage fell, otherwise power factor deviation, harmonics. There are so many power quality issues which comes into picture when we want to integrate this DG into the main electric grid. So such things we need to be taken care of. So that's a very important things. And maintenance and protection and synchronization. See, when we create a DC microgrid to put and that DC grid integration into the main AC grid, so we need to have conversion, DC to AC conversion by using inverter system. And once we convert the DC to AC, then that converted AC is it should be of grid frequency level. So then only we can see the DC, what is that? The integration into the main grid is in synchronization. Otherwise, it fall off on the out of synchronization. That means the grid frequency is very important thing to be taken care to interface the DG system into main AC grid system. Okay, yeah, these are something, some basics of what is this electric power grid system like AC and DC grid. Now the thing is, okay, when we in these things, what are these DC systems, DC grids can be utilized at, and what are the storage levels which can be normally used, and what is their voltage level and current level? Because see, when we say that UPS will have a battery, and UPS will comes with the 12 volts battery, and most usually, and then hybrid electric vehicle, fuel cell electric vehicles, or PV or fuel cell combined, and telecommunications and energy storage, and in most of the things, okay, which is what is this voltage? What I am showing here is of a DC voltage. Okay, in a UPS system, 12 volts battery, hybrid vehicle system, so 48 volts. It all depends on the even the whether that is a what type of vehicle, like whether it's a light vehicle or heavy vehicle, medium vehicles, and so on and so forth. So based on that, this the storage system, battery level voltage, the DC voltage levels are used. Now, so yeah, here you can do notice this hybrid energy interface. Here we have a very clear clarity about the various paths and various conversion pattern. See, now suppose if we do consider this is the one AC main grid, AC grid, and this is the PV source, and now where this is the battery storage and inverter to feed the again electric motor, and the any other auxiliary loads. This is particularly, of course, what I have taken. And propulsion system, of course, as we our now our theme is like electric vehicle system. So this schematic, it gives the clear idea hybrid energy interface in electric vehicle systems. What is actually this will do? This will do accommodate the variability of the different energy sources, and it match the specifications of the various loads, and it provides the power conditioning. Power conditioning is something like maintaining the voltage level, and conversion and control. Conversion and control. That is the power conditioning circuit. Of course, it is basically a converter and control. And then the regulation, the voltage regulation, and then the power flow control. Power flow, of course, it can be of either like charge or discharge. So it could be of a bidirectional power flow. So this energy system, it can provide a power flow control. All these aspects will be taken care of this hybrid energy interface in electric vehicle systems. And also, what is this auxiliary loads in electric vehicles I am talking about is, now our problem is in electric vehicle systems, it's not just only the propulsion system. Apart from these propulsion systems, we have other auxiliary loads like lighting, audio systems, steering systems, and whatnot. Okay, there could be of different, and even nowadays, of course, AC. All these are the auxiliary loads, and for these auxiliary, most of the auxiliary loads, like say audio system or steering system, these are of maybe of like a DC loads. Okay, for which, and even the, nowadays we are talking about the LED lighting system. Most of the vehicles is now in the vehicles now see the most commonly used now in the vehicles is eye bright LED lighting systems. So which is basically of like a DC load and which needs a DC, and that could be also be one of the auxiliary load. Okay, like that there are various auxiliary loads in the vehicles for which auxiliary power supply is required and which can be provided through a auxiliary power conversion. And see, the another main thing is that here, what is that I can show here, it is that, see, the grid, it can be, yeah, we have a storage system here in this hybrid energy interface. So here we have the main grid. Even suppose if your vehicle, see, vehicle battery need to be charged. So it can be charged from the main grid on, okay, or from the other off-board charger. So means from the any other solar charger. Because, yeah, here we can see the solar system, and from the solar panels, okay, through a MPPT charge controller, okay, it can able to charge your battery. Also, some part, okay, it can also be taken from this grid. That's fine. Suppose if your battery is fully charged, then so what is the need? So, and that can be cut off from the charger. But however, your vehicle need to run continuously. But say that can be yes, feed from the again this charged battery to the vehicles and also to the auxiliary loads. Suppose your vehicle is at stop, your vehicle is not under operative, then whatever the stored energy in the storage device, that is a battery, which can also you can give it to the grid. So that means you something like you can sell your vehicle, the power from your your vehicle storage battery, vehicle battery storage energy can be given into your grid also. That is so called vehicle to grid. So whenever we want the power to your vehicle, we can take it from the grid. Whenever there is no need of your power, say the power to your vehicle, but your vehicle is under stop mode, that means not operative mode, then you can give it back whatever the energy is there, which can also give it to your grid also. So you can also charge, you can sell your power. Okay, suppose your vehicle has a PV panel, you can small panel, okay, you can create and you can generate some energy even during the run that can be put into the battery, and but once that you have, so that can also you can give it back to the grid as well. Okay, so either the system, so this is also possible. That's why we call it as say grid to vehicle or vehicle to grid. So this is another very interesting thing nowadays. Okay, what we can, it's not only that we can take the power, we cannot power from the only power grid, but from your vehicle also you can give it back to the grid. Okay, that is so called vehicle to grid or simply V to G. This thing. Next, next it become see, when it comes to the systems. Okay, what are these electric vehicle systems? You can just have a hybrid electric vehicle systems, wherein which of course we can have a conventional engine, IC engine as well, along with your electric battery as well, the storage. So that storage system, it can also be charged. It can be assisted to some extent. So whenever it needs. This is the one. See the new path to introduce these technologies in vehicle systems for fuel savings, and also it is a cost-effective, pollution-free, effective harness of energy resources. And however, this concept, because when we need to have this both conventional IC engine as well as the electric power into your vehicle, of course we can focus on these medium size and large scale full hybrid electric vehicle systems, no doubt. And that is the thing. And another class of electric vehicle system is plug-in hybrid electric vehicle systems. What is this plug-in electric vehicle system means? Yes, of course, wherever it is, of course, this can also have a IC engine, but it can also be a purely electric vehicles. It only depends on your energy backup. Okay, that means energy storage in your vehicle system. So, but this can be, and it is not just that something like we can have this standalone powers on your within your vehicle, but wherever the charging station is there, we can go. You can just go and you can just charge the vehicle, and you can pay for that whatever the amount of charging and charging time so that you want. So then we can opt it. That is so-called this plug-in charging. And here the power flow management and utilization of grid to vehicle and vehicle to grid. As I told you, here in this plug-in hybrid electric vehicle systems, you can charge your EV from the grid as well. You can also give give back the excess power or any unutilized stored power from in your battery system of the vehicle back to the grid. That is so-called vehicle to grid. Okay, so utilization of grid source to vehicle as well as vehicle energy in the energy stored in your vehicle storage system can also be given back. You can sell it back to the grid as well. So that's the advantage of this plug-in hybrid electric vehicle systems. And what is the specific needs, including charging, voltage swings, highly specific thermal control? Okay, here there are some issues which need to be taken care. So all these in this plug-in hybrid electrical systems, because when the main thing is that suppose when you transfer the power from your storage of your vehicle system back to the grid, as I told you that it has to be taken care by the various aspects like frequency, voltage level of the grid system. So that is a next. Yeah, other kind of vehicles, other kind of electric vehicle systems is of fuel cell vehicles. Here, of course, fuel cell vehicles means we are targeting towards the compactness of the vehicle systems when we are powering from the electric power. But the thing is that here the fuel cell, as of now, the fuel cell, the cost and reliability is the major issue of this fuel cell system. So what we heard about, that's fine. And next, basically, as I told you some sometime back, the power the various loads in this electric vehicle, like and from the various resources, the management of this power, which needs a multi-pole or multi-voltage bidirectional power converter. That is a very important part of your any electric vehicle system. It is. So what is actually here? It is that So this multi-port bidirectional power flow DC-DC converter so will play a major role by taking the energy from the energy resources and converting into the required form and to the required level, and it can give it to the traction motor, and also it will also feed the any other auxiliary, because we can multi-voltage level means see we can have a multiple output converter system. Then that multiple outputs which can be met to the need of the auxiliary loads, okay, like audio system and the lighting and AC or any other so on and so forth in the vehicle. That is how. So this bidirectional multi-port DC-DC converter will plays a vital role in the electric vehicle system. Because in this bidirectional power flow means, see here there is a storage device. So to store the device, to charge the storage device, it need to take the power from one direction, and again to take back from the storage device, again the same converter. We no need to have a different kind of different converters for different paths. So that's what I am talking about. Both the direction, forward direction and reverse direction. Suppose if I say the charging the battery from the solar or fuel cell stack means, so convert your fuel cell energy into the required DC voltage level, and then you charge the battery. And then once the battery is fully charged, of course, then there is no need of this. And then you can see the thing is that whenever you want that the charged energy in the battery, which can we take it back to the loads, that is again from the same converter. So in the reverse direction of the power flow, reverse direction of the power flow. That is so called, it's a bidirectional power flow. So then that power which can take it from the storage and it can convert again, that path is nothing but discharge path or discharge operation of a converter, discharge operation of a bidirectional converter. Then that taken from the battery and it is given to the loads in the vehicles. That is what is it is bidirectional multi-voltage DC-DC converters. Next, these hybrid electric vehicles can, what is this, the best part of this hybrid EVs is these hybrid EVs can overcome that instant charging and reduced top speed and much distance coverage for charge and convenience and non-reliable and battery depletion issues. So these are the various issues in our electric vehicles can overcome by these hybrid EVs, because there is a different resource. Hybrid means it's like a combination composition of the various resources and the storage devices through power conversion stage. So hence some of the issues of very important issues can be overcome with this hybrid electric vehicle systems. Yeah, so this is something like, okay, just a typical what is this in the electric vehicles? What could be the configuration of the power configuration? Where is your power converter? Where is your battery? Where is your fuel source? And where is the motor? So that motor, which of course, which coupled to the propulsion system of the vehicle system. So all these things that we can clearly notice here in this case. So EVs, okay, that is a power converter and energy storage in EV systems. As I told you about, yes, there is a battery and bidirectional converter, bidirectional power converter, and fuel cell. Fuel cell is the energy source, and again from the fuel cell there is a inverter. So fuel cell, from the fuel cell source, it can give directly to the motor by the way of converting AC to DC, DC to AC, because the motor used in the propulsion system may be, it can be of AC. Of course, it need not be of AC. It can now see, we can also think of the DC motors as well. But DC means they're like a permanent magnet, PMDC, PMSM, even switch reluctance motor. All such sort of motors can also be used, where in which the direct DC from the DG and distributed energy sources can be directly convert in the DC form, and we can be given to the this type of motors, DC excitation motors. But here in this particular system, what we look at here is DC to AC inverter. That means from the fuel cell, it takes the DC and it converts and it gives it to the AC inverter. Then the bidirectional converter. Bidirectional converter, of course, it can charge the battery from the fuel cell stack. So that again it converts the required level of DC voltage of the battery. Then it will charge the battery. So it means it can supply the motor as well as charge the battery simultaneously. So that is what these two converters will do here. And of course, for the fuel cell stack, the energy supply is from the hydrogen fuels. Of course, we know that the hydrogen fuel cells and the fuel cells, there are various types of fuel cell systems, as we all know about. Here this hydrogen tank, which is used to feed that hydrogen to your fuel cell system. That is how, okay. These are the inputs to your fuel cell, and then from the fuel cell output, it can able to give the electric signal, okay, voltage current, and that can be taken into the converter input, and converter will do the conversion of AC DC or DC AC or DC DC, whatever it is. Next is also a similar type of like this is another block schematic of the electric vehicle system, wherein which the fuel cell is the main source, and from the fuel cell it converts into the required voltage level, and it will charge the battery. And now you can see the battery here, which is a low voltage bus. And suppose if you have a fuel cell which provides the higher voltages, of course it need to step down the voltage level, or if it is provides only lower than the 12 volts, then it needs to step up the voltage level to 12 volts, and then it needs to supply this the required battery voltage level and vehicle load level, voltage level, all these things. And at the same time, see the controller and this main AC DC grid. This is so-called DC now here. After conversion of fuel cell energy to the DC, electrical energy, it is a DC grid. This is a high voltage bus. From the high voltage bus, it will step down the voltage level and it will charge the battery, as well as this high voltage bus, which is required to convert say into the AC type support, because most of now currently most of the electric traction systems, okay, they use AC motors. Therefore, so we need to have a conversion from DC to AC. So this high voltage bus is directly fed to the inverter system, that is a DC AC inverter, which is a called traction inverter, and which is given to the motor, electric motor, that is the AC motor. So that's why it is called inverter here. It is okay. Yeah. And this is another thing is that power converter and energy storage in LPG systems. And as I see, as we discussed about the plug-in, in the plug-in electric vehicle, see, of course, uh, from the AC plug-in to the what is that, a grid. So from the grid, we need to have a AC-DC charger, and from this, after conversion of AC to DC, then again we need to have another converter, say, in order to provide the different voltage levels, and also to charge the what is that, storage system, and also to supply the motor. But here the challenging thing is that the see, the control part. Okay, so and control part, and also provide the sub voltage levels for all see other auxiliary loads in the electric vehicles. Therefore, here this controller, yes, the control platform, of course, that can be realized in the different platforms. It can be already mostly now digital controllers are the best suit than the analog controllers because of high speed and parallel processing and multi loops, multi controller. Okay, multiple controllers can be taken care easily with this digital control platforms. So that's the thing. And but this has to be this plug-in hybrid vehicle systems. The converters must be, even the AC/DC charger must be of a bidirectional charger, bidirectional rectifier. It should be. It should convert AC to DC as well as DC to AC. Because when you want to charge the or feed the power from grid to vehicle, you can take it from the electric grid to the vehicle. So in that way, you can do convert the AC to DC and DC to AC again to the inverter level. And again, when you want to give it back from the vehicle energy to the grid, then say that need to take the power from the vehicle storage system, and it should convert and it will give it back to the grid, and that is the way. Okay. But so in that case, that conversion, power conversion should be in bidirectional here also. Yeah, this is a typical charging station, electric vehicles charging station. So in future, of course, we also we may see in most of our petrol bunks will come out to be like a EV charging stations, EV charging bunks, not the not only the diesel and petrol, but also electric power charging stations. And here we have the one other, what is actually the specialty here you can do see understand here is that you can see it is a solar roof. The charging station is a solar rooftop. It is like, and this is a standalone because it no need to have a what is that? This solar charging station, no need to connect it to the grid. It can be a standalone. It is completely standalone. That's why it is nothing but independent of a grid. So this standalone charging station by means of a solar, fuel cells, even wind, all these energy resources can be utilized to create a standalone electric charging stations in the transportation systems. And this is more viable and feasible for the transportation systems, because wherever we need, of course, we can just make a sub parking stations, sub charging station, just like our what is it, petrol bunks or something like that. So we can have station, number of charging stations, which can be completely independent of the main AC grid. And these are most suitable for the commercial parking slots or municipal parking slot, that is in the public systems, okay, public places. So these are most beautiful options for the electric transportation systems. Okay, so now the main thing is, okay, what is that? Yeah, I just discussed about what is actually the electric power, and what are the types of power grids, and how to what is their role, and what is their configuration, and what is power management in the electric vehicle systems, as of now. So in the previous discussions. But now when it comes to the converters, now I'll just talk about purely this power converters part. Of course, I'm not just going to deep into this very deep analysis of the converters, only the fundamentals of our power conversions systems, okay, that we can talk. See, basically, when we say, okay, these most of our say energy sources now we do utilize of like a PV, fuel cell, all these things there. And as I mentioned about, in future we can also have a say this DC motors, okay, DC excitation motors like okay, special PMSM, permanent magnet distribution, PMSM, and PMDC. Next, switched reluctance motors, all these, okay, which can be excited directly from the DC. So therefore, in future electric vehicle systems, so maybe these motors, DC excitation motors, becomes more popular in the vehicle systems. Therefore, okay, I focus much upon basics of the DC-DC converters, okay, for solar and fuel cell applications. What is actually here is that these converters can have a better efficiency curve, and near DC is nothing but almost see DC. Most of the people, what they do understand, when we say DC, okay, it is just direct a straight line kind of signal, okay, straight signal which is out. No, not like that. Suppose if I consider a rectifier, so for example, we all know about the rectifier, right? So if it is a rectifier, AC, after converting AC to DC, okay, we call it as that signal because the signal which is after the rectification is just only on one side. It's not like on both sides. Like in alternating, there is an alternate positive signal and negative signal. Positive signal, negative signal, that is in alternate. But in the DC signal, it is one direction. It may be only positive DC or only it is negative DC. But but when we say the DC, it can be a pulsed DC or steady DC source, or but most of the time we need to survive with see the average DC with AC component. The simple thing what you do understand is that we have a diode rectifier. From the AC, you are converting to DC from the diode rectifier, and immediately after your diode bridge, you will see the sinusoidal signal which is turns out to be in only one direction. Suppose if you take a full wave AC full wave rectifier, so it is turns out to be a DC one direction signal, but which is not purely what is that? Average DC signal, but it is so-called AC component. Then what we say, the average component of this pulsed DC, it is like, okay, it is actually the DC. Okay. But to remove that AC component in your rectified DC immediately after your rectifier bridge, we use a low pass filter. We use, because we need to remove that AC. That's why what is that we use a filter capacitor. Once we put a capacitor after a rectifier circuit, then you will see the DC signal which is of the pulsed DC, that is, which is a sinusoidal pulsed DC after the rectification, which is turns out to be a nearly a ripple-free DC value, but otherwise still it will have some AC component. That's why we call it as near DC input signal, not exactly a DC live. Okay, and use of this conversion, we can have a better source utilization and reduced current test and conduction loss because of the advanced technologies, semiconductor device technologies. That means normally most of our converters, we do use semiconductor switching devices. So because of the advancement of this semiconductor device technologies, so the conversion efficiency can be improved significantly. Then integrated boost feature reduces the transformer size, because no transformer like a power transformer, like a power frequency transformers, which is of like a large size. So that is depending on the kVA rating of the system. So the transformer size of 50 hertz, which is, of course, we all know about. But when we talk about this in the DC-DC conversions, we can have a say high frequency conversion, high frequency inductors and transformers as well. That is another best part of this conversion system. But one issue is like in the conversions is like okay, conduction and switching losses and duty cycle loss and ring. So some secondary ringing, all these things. Okay, which comes into what is that feature in this conversion process. However, of course, these things can be taken care to some extent by means of various techniques that we have. And moreover, this converter can be able to give a flexible voltage levels and also in a regulated manner. Even suppose if you have your source voltage is varied, but we can only maintain the regulated voltage at the output of the converters. That means even the wide variation of the source voltage or the power load variations, which can be taken care with a proper the suitable controller or control circuit in the power conversions. So that is another beauty of this power conversion systems. Yeah, these are just simple basic power converter topologies. Our electrical engineering people, so okay, they do understand these things. Of course, it's not that only circuit people can understand, but others also, if they know something about some background of the circuits, because most of all engineering branches, they do study some circuits in the first and second year probably. So definitely, but otherwise, when we say these converters, okay, they may be surprised, okay, or wonder that okay, what is this? But it is nothing to panic but anyway, the beauty of this power electronic technology, so it makes your simple passive converters, passive circuits, passive networks like electrical circuits into like active electrical networks or circuits. So now I call it as therefore I can say this converters, this power converters is of active power circuits, active electrical circuits. So in general, I can call it as. Here, say as I told you that, say the DC-DC converters are basically as of like say I have three types. One is buck converter. So buck means it is a step down converter. So you better understand if I say the step down transformer, step up transformer. Okay. So uh, in our electrical systems. So these are also this buck converter means is a step down converter. Something like it is a step down DC transformer. Boost converter means it is a step up converter. That means output voltage can be increased from the lower input voltage. So that's why it is so called step up converter, or in the power electronic terminology, we call it as a boost converter. And whereas the other one topology is okay, the converter which can do either step down or step up, then we call it as it is a buck boost converter. Buck means step down, boost means step up. So that is it. And next, yeah. So this buck boost, that is step down and step up operation. It depends on the duty cycle of the our switch. This is a semiconductor switch. This is a transistor switch. Normally we use MOSFET switching device. Because we know BJT, bipolar junction transistor, MOSFET, JFET, like that, IGBT, all these things. Most of us we heard about, and it's more of course those electronic devices, electronic switching devices are used in this conversion process. That is what this, and the duty cycle of those electronic devices will be modulated, means will be adjusted in such a way that so to do the required energy conversion or power conversion process. By the way. Next, so of course there are various class of converters. These converters can be of isolated or non-isolated converters, or it can be single-ended, double-ended converter, or soft-switching converters, and voltage-fed, current-fed converters, low frequency and high frequency converters, pulse width modulated and resonant converters. There are various classifications and the configurations of power converters are available. So it can be utilized in any type of power conversion process as per the required power process. It need not be like only AC to DC conversion or DC to AC conversion or DC to DC. Any sort of conversion, okay, no matter. But say in these things, these DC-DC converters can be also we can utilize effectively with various features. Yeah. Basically, yes. Now we mostly what is that? We use high frequency of operation for this power conversion process. Hence, these power converters are so called to be high frequency converters. Why this high frequency? The term high frequency. What is this high frequency? Is nothing but okay. Usually our frequency of the grid is 50 Hz. Our grid operating frequency is 50 Hz, but that is power frequency we call it as. Okay, this grid frequency of grid operating frequency 50 Hz is nothing but a power frequency, and which is a low frequency. But what is this high frequency? What it comes in this electronic system, power electronic system is this is because of the various reasons. Because what is that main thing is that, see, it is because of the high frequency magnetic materials what we do use, which helps to cut down or reduce the size of this reactive elements which is involved in the power electronic systems. Say like in a converters, we do use mostly this high frequency inductors or high frequency transformers and high frequency this filter capacitors. So the very reason is that these magnetics and are significantly reduces the size of this inductors and transformer size while providing high power density, while providing high power capability and handling capability. That's the very best part of these high frequency magnetics or high frequency inductors and high frequency transformers. That's the very reason why we do use this high frequency operation in this power conversion process. Therefore, so we simply call this power electronic converters. Most of the DC-DC power electronic converters are of high frequency converters. And moreover, now due to this the material technology, the development in the materials, material science, so even nowadays there is a huge improvement in the performance of the available magnetic elements and the reactive elements like capacitors and resistors also, so on and so forth. So and even they come with a very lightweight and with a cost, low cost, means affordable cost. So yeah, it comes with very handy. Then yes, this high frequency magnetics are the main motivation for the, the compact power supplies. That means to design the power converters with varied scale. Okay, even from the low power fractional watt to kilowatt power levels, we can able to design converters with high frequency magnetics and filter components. So that's the very best part in this power. That's the reason that why these power converters are more becomes very popular in most of the applications, not only in the electric vehicle systems, in most of the any other things. Okay, domestic, you take the domestic system or industrial systems or anything else. So next, yeah. So here I discussed about the DC-DC converters can, this power converters can operate with either with hard switching and soft switching. What is this switching? The switching, of course, here this is a MOSFET. This is a MOSFET electronic device, and which can operate as we know that the VI characteristic of the MOSFET, as we study in this what is that basic electronic course in the primary course of our all engineering branches. So yes, we can do understand better if I say it that way. So, but the word what we do use this hard switching is that, see, when we do turn on and turn off these electronic switch, there is a changeover of current and voltage simultaneously during turn on and turn off. So there is a simultaneous changeover of voltage and current, which leads to the power loss in the power conversion process. That's very what is that? Basic reason that any efficiency decrease in the power conversion process. That means because when we go for high frequency operation, the turn on and turn off instant of the switch depends on the operating time of your power converter. So suppose if I operate for 1 hour, but if your converter switch is operating with a high frequency of like 100 kilohertz, 100 kilohertz means what is, say for example 50 kilohertz. 50 kilohertz means 20 microsecond. 20 microsecond is the total time period of the switching operation. So, but the 20 microsecond switching operation, if I keep that converter is for like a 1 hour, that means in 1 hour operate this thing, how many cycles your switch needs to come across. In those many cycles, the number of turn on and turn off instance is taking place. But due to this simultaneous changeover of the voltage and current during this turn on and turn off process of a device, which leads to a power loss, which is so called a switching power loss. Switching power loss. If there is a switching power loss, that leads to the decrease in the efficiency of a power converter. So that is what actually. So that the thing here is this hard switching of a converter. That means the hard switching naturally, so it leads to the decrease in efficiency of the power conversion process. But to extent we can, it is not that we can completely eliminate the switching loss, because we have to survive with it. We cannot be too satisfied for like, okay, your device should not take any input energy, so it has to give complete energy. Whatever the input source you are given to the converter, you cannot expect 100% output power. So some energy consumption that some energy buffer should be given to your power converter devices as well. So that's the thing what we need to be understand here. So, but however, to the extent we can minimize or reduce the switching power loss in the power converters, so that the efficiency of the power converters can be improved or increased to the possible extent. So that is possible. That improvement of efficiency of the power converters is possible by using the other kind of switching. That is so called soft switching. Okay, soft switching means wherein which we can turn on and turn off the device when the voltage across the device is 0 or current through the device is 0. Then which is that instant of switching is so called a soft switching, because there is no simultaneous changeover of the voltage and current during turn off or turn on process of the power device. Therefore, the product of this, the voltage and current is power. Obviously, if there is a 0 voltage across the switch when the switch is turning on, so then the turning on loss will be reduced. That's what we can do. Understand a soft switching so called. Anyway, that soft switching approach can be used in most of our power converters. Of course, we do use that soft switching techniques in most of our power converters design, so that the converter efficiency are improved significantly. Then Okay, what is the effect of this high switching frequency? Yeah, as I told you that the effect of yeah, here you can do understand the importance of this switching frequency plays a role in efficiency aspect. If the switching frequency, say for example, let us consider a switching frequency of our electronic device, that is a MOSFET device of 100 kilohertz. Then say okay, we can do evaluate switching losses of say for example 1% switching loss and also conduction loss. It is not only that the switching loss will exist in the converter, but also conduction losses are also there. What is this conduction loss means? When the device are in complete conduction, so during that time also there is a what is it? Some residual voltage, the device voltage drop and the current through the device. So that leads to the conduction power loss. So that is so-called a conduction power loss. And we do use transformers, inductors, filters, all these things, and resistors. Okay, if we do consider all these other passive element and losses in the other passive electrical elements, which is considered to be 1%, say for example. So all put together, now the total power loss in my power conversion is it could be of 4%. 4%. No, this is just to make you understand what is this switching frequency and how this switching frequency plays a vital role in the efficiency of the power conversion. That's the only reason here I'm just discussing here. So if there is a 4% total power loss in the power converters, but you get only 96% efficiency. Then, so for example, now you further increase the switching frequency to 1 megahertz. Same converter, don't change your converter, but the same converter only, whatever the device is, but only the frequency of operation of your converter is increased from 100 kilohertz to 1 megahertz. So with this increase in switching frequency, the switching losses will dominate. That means switching losses will further increase as compared to 100 kilohertz frequency of operation of the converter. And obviously, again, the conduction losses will also increase. And say, okay, if we take other passive elemental losses to be unchanged. Unchanged means okay, because other losses, passive transformer and filter losses, it's not directly related to your switching frequency. So therefore, okay, considering these losses to be of only 1% loss, but there is an increase in switching loss because of the increased switching frequency. There is an increase in conduction loss. It is maybe because of the increase in the duty cycle or okay model the radius. But because of this increased switching loss and the conduction loss, the total efficiency, that means the overall efficiency of a power converter will drastically down. Drastically it will come down. So almost if you compare to this 100 kilohertz frequency of operation with 1 megahertz of switching frequency operation with the same for the same converter, the efficiency will come down from 96 to 86%. So this is the disadvantage. Okay, okay. We cannot say disadvantage, but for that we cannot just go back for the low frequency operation of the converter, because high frequency operation will have a other advantage of reducing the magnetics and filter components of the power converters. So that way it will reduce the total overall size of the power converter, but however which leads to switching power loss. But the switching power losses can be cut down or minimized with some other switching techniques. Okay, that we do what we call it as a soft switching technique or resonant switching techniques. So with kind of some this switching methods, the power conversion efficiency can be improved upon in many converters. That's the thing. So, but what we do understand here, it is that this high frequency operating converters are of low efficiency, large and heavy heat sink. But anyway, yes, if there is so much of amount is heat loss, this power loss is so happened that power loss will also lead to the generation of the heat. So where to dissipate that heat? So we need to have a heat sink. Heat sink, okay. So we have to provide a some kind of cooling mechanism or heat sink element in the converter. Anyway, that is taking size, but this heat sink size, the size of heat sink is also increasing as the switching frequency of the converter increases. Okay, therefore, the optimization of the switching frequency design for any given converter is also very, very important. It's not just like, okay, we have an advantage of cutting down the magnetic element size with the higher operating switching frequency. So just like we cannot go far, but anyway, we have to see the negative part of that increase high frequency operation. So that high frequency operation, it leads to low efficiency because of higher switching power loss, and which increases the heat sink. That's it. And obviously it reduces the source utilization, so that effective source utilization may not be possible. So, but all these also issues also has to be addressed by means of some other various approaches. That is also possible to the extent, because in most of our converters we do able to achieve more than 90% efficiency. So that's the thing. Up to even 98% is possible because of the advanced other switching techniques which can be used, and also the advanced devices. It comes into the technology nowadays, like even our conventional transistors also are of improved versions with the semiconductor material technology improvements. Now we have like silicon carbide devices that are much more popular, which can able to operate even with even a very high frequency, but with minimized switching loss. That's the thing. So that advanced devices are also available in the present day, which can be best utilized for this power conversion process. Yeah, so that is all I was talking about. That soft switching, see, hard switching will leads to the lower higher switching loss, hence the lower efficiency and the higher heat sink size. But to encounter that the drawback of this hard switching frequency in this power conversion process, to improvise the efficiency, we can use the soft switching and which to realize the compact and low cost and light weight converters, power converters. So I was talking about that. Okay, what is that soft switching there? Soft switching means, yes, the voltage and current will be zero during the turn on process of your device. If you do, if you look at here, in fact, see the turn on process here. See the switch voltage transition and the switch current transition, but this is the switching pulse you are given to the gate terminal of the device. So at the momentary, when you give the gate signal to your switch, the voltage across the switch, the blue line is the voltage, and this is zero. And then at the instant when you give the gate pulse, even the current in the device, means the device is completely open. As well, the voltage across the device, the voltage across these two terminals, okay, this is also zero. Hence, if I turn on your device during the zero voltage and zero current instant, that could able to provide the zero, zero power switching power loss. That means voltage is zero, and the current is also 0, then the P is equals to I switch into V switch. So then, yes, if both are 0, this is 0, then the power loss is also it's going to be 0. So then, yes, I can say it is 0 power loss. Okay. Then I call it as here power loss. That is the switching power loss is going to be 0. Similarly, during the turn off of this switch, this is turn on. Here this is turn off duration. Okay. This is turn on duration. This is turn off duration of the device. When you do turn off the device at the instant where the switch through a device, that means this is I switch and this is V switch. Okay. If this I switch, the current through the switch, because the switch is completely opened, when the device is, when the gate pulse to your terminal is terminating, this is the terminating point of the gate pulse here. So at this instant, the switch is completely open. That means the current is completely 0 here, 0 current, right? So I current, I is 0. Again, the voltage, the blue, this is voltage, V switch. This is also, this V switch also 0 during this turn off instant of the device. Hence, obviously, what is this, your switching loss? Because when the voltage is 0 and current is 0, then your gate terminal. So, okay, the pulse, what is that you are giving? This gate pulse, this you are terminating to the device. Hence, your device could be able to turn off comfortably without having any residual voltage across the device and the current through a device. Hence, the switching loss is going to be 0. But anyway, this is for ideal condition. Okay, this is for ideal condition, for the ideal design. But in practical, it is not. In practical case, it is not. We cannot achieve the exact 0 power switching power loss in practice. Okay, so then we need to take care of that. So whatever the best possible design, okay, to improve the. But once if yes, the switching power loss is increased because the efficiency is output power and by that input, okay, this output plus power loss. Okay, but here in the power loss, if power loss is equals to 0, this is ideally right, then efficiency is going to be 100%.
Sir, we are not able to see your markings, sir.
Is it so?
It is not
Hello?
visible, sir. Your markings are not visible, sir. Whatever you are writing, it is not visible in the.
Acha. Okay. Then it's fine anyway.
Okay, sir. Shall we start the question answer session, sir? Any?
Yeah, so now, oh, my time is lapsed.
Yes, sir.
Okay, then sorry. Okay.
You can conclude, sir. No problem, sir.
Yeah, so let me, so is it possible me to continue first?
Yes, sir. Yes, no problem. Another 10 minutes you can continue, sir. No problem.
Okay. Okay. Then yes, just I wanted to give some, of course, for our friends it may be useful. So what are the directions in the research directions possible uh, in these power conversions for electric vehicles? The bidirectional converters, there is a huge scope in many aspects, okay, in most of the applications now we need to have this okay, these power conversions, especially this bidirectional power flow converters. And as per the research point of view, okay, there is no say limitation to explore the new converter topologies with high power density and high efficiency and reliability and effect of charge discharge current, because this is very important. This, because in our vehicle systems, this charge and discharge current is the most important crucial thing, one we need to concentrate upon, of course. That is, and also to enhance the power flow control and efficient power management, okay, in the vehicle systems. These are all these okay, issues. But yeah, this is for like, suppose if we go for any grid fed charging systems, then the power quality issues. Because what I need to say here it is that if the quality of the, suppose because of your vehicle charging, if you pollute the grid power, that means if you make the poor power factor of your grid, then we need to pay for that also. So means as the power rating, okay, increases, the cost and complexity of this improvement of the power quality is also increases. Okay, so this thing has to be taken care. Suppose when we go for this onboard chargers, so when we charge the vehicles from the onboard grid chargers. Okay, then anyway, there is a very important thing is what we need to understand here in this battery charge and discharge power conditioning in electric vehicle systems. As I told you, for a grid fed AC DC rectifier with power factor correction, because here we come across with sinusoidal current in the AC grid, but when if the load is of like a DC, then that any impact of that power factor reduction or power quality, this need to be taken care for the grid fed AC DC chargers. Usually, okay, rectifiers are constructed with the passive devices or with the active devices also. It need not be lowerly diode rectifiers, which can be also the control rectifiers. We can design a rectifiers by using active devices like okay, BJTs, MOSFETs, and this what is that, IGBTs, and so on. So. And bidirectional converters, of course, it is just bidirectional. It is a only single entity. Bidirectional converter is a single entity, but it can provide the power flow in either direction to charging the storage system and discharge the storage system to feed the load. Okay, as and when it required. But this during this charging and discharging mode of your battery in a vehicle system, so there is various aspects that you need to be taken care. So what is the charging time? What is the your see the discharging time, and what rate we need to charge, how fast we need to charge, and also during this see there are even during charging and discharging there are different levels of okay charging, see voltage levels or current levels. You can say fast charging and slow charging. That depends on the battery current. Okay, the charging current level. So obviously, faster charging requires high current charging will go for fast, but we need to pay more. So there are various aspects, and also during this charging discharging operation, lot of the heat is going to generate within the battery, and that heat management. That means that we need to protect the battery also from the there are some of the issues. So then there is another thing which is so-called a battery management system. Battery management system becomes a very backbone of your power management in the electric vehicle systems, where we do use battery storage system. Because we need to essentially we need to use a battery system in the electric vehicles. Obviously, these are the things that need to be taken care of. Yeah. So anyway, these things only our electrical engineering friends can understand. Just only to show some how looks the power converter configurations. Here, the converter, it could be, yeah, it is a PWM rectifier. It is the AC grid. So this converter is fed from the main AC grid. It converts AC to DC, and then from the DC to again the DC, because mostly the battery voltage levels, battery voltage is maybe 12 volts, 48 volts. Okay, as we discussed about in the previous slide, the battery voltage levels are usually not too high, like hundreds of kilovolts. It cannot be like that. So, but there are like low voltage levels, but high current capacity. Like ampere rating is only the this deciding age rating, ampere hour power rating of the battery decides the size of the battery, not the. So then to step down that the rectified DC voltage, because here 230 volts is rectified to say √3, because if it is a full, this is a PWM rectifier. Here we will also have a say the flexibility of stepping down the voltage of this 230 volts RMS to in the DC-DC conversion, of course. See, because here also we can able to control these devices as it is a PWM rectifiers instead of diode rectifiers. If it is only diode rectifiers, then we cannot able to control whatever that rectified voltage. It could be of √2 VRMS by 5, as it is a full wave uncontrolled rectifiers. So, but that amount of voltage that need to be stepped down to the battery voltage level of 12 volts or 48 volts. So then again we need a DC-DC converter. Simple concept. So these are just to make you what is this configurations, AC-DC configuration, DC-DC configurations of power conversion systems. Yeah, so when I was talking about, I was telling about controller. Control is also okay. These are very much required to maintain the power factor and also to provide the regulated voltage and current in the charger circuit. Obviously, we need to go for a controller in the converters. But anyway, there are various types of controllers which can be designed depending on our power conversion configurations. That is the other issues. Next, yeah, this is a AC-DC converter, and here the DC-DC converter. Again, in the DC-DC converter also we need to have a controllers. If it is a bidirectional converter, we need to have two controllers. Okay, the controller for forward direction, controller for reverse direction. That means the charging path controller, discharging path controller. Of course, anyway, we did simulations of this charge converters and discharge converters. These converters for charging, discharging applications in electric vehicle systems. So see, you can look at here in the simulation, in the results. See, this is the supply voltage and supply current. That is a grid voltage and grid current, where in which you can see that in this converter can able to provide a both the voltage and current are in phase. So that means okay, my charger circuit is not disturbing the grid power quality. So it is maintaining the power factor of unity, because both the voltage and current are in phase with the they are in phase. Hence that cos phi is going to be 1, because the phase angle is 0 between the voltage and current. So hence I say, okay, so quality of the grid is not disturbed even when you charging the your vehicle storage system. So like that, of course, we have all these. See, this is a battery current, battery voltage, and battery current also, which is shown. But here, if you look at this, there is a ripple AC component. See, average current is 10 ampere, but however, there is a AC component of see plus or minus some 2 amperes, something like that on either side. Sorry, 1 ampere. Approximately, not only, but is less. But anyway, that ripple is also plays a very role in the charging and discharging path. But again, which leads to okay some other issues. Okay, this is a charging mode results of a converter, and okay, but maybe our faculty of electrical engineering can understand better. So these things. And here where there is a mode changeover. So as a this is a load, okay, battery load changing conditions, and again the discharging mode of operation. The discharging mode of operation also, of course, see the voltage need to be maintained. So good results it gives. Okay, yeah, both grid and. So this is from vehicle to grid. Suppose when you want to give back the energy which is stored in the storage system of the vehicle. So again, of course, you can operate your converter in the reverse mode, and okay, you can give back to the grid also. But during that time, of course, see it is taking the negative. Okay, yeah, negative power. Power negative means you are just okay, giving back. It's not the consumption, but it's putting into the grid. Okay, these are some results, and here also you can look at the THD, because this is very important. We need to follow the standards, IEEE or IEC standards of the okay, so the various standards to follow the limitations of the various power quality issues like total harmonic distortion, THD, or power factor, all these things, okay, that we need to be maintained. So within, but otherwise, if I want to say here this 4.4% of the THD, so it's a very good thing, say, which is very much less than very low value than the limitations value. Usually the limitations as per the standards, which is up to 5 to 8%, that is mostly we can have, but this is much significantly less than the standard limitations. So these are the issues that we need to be taken care, and these are very important in the vehicle systems, especially in the electric vehicle system, because we are all talking about only electric vehicles. When we do design, okay, talk about electric vehicle system, the power converters are very important aspect. This is one thing, battery management system. When I was talking about okay, battery storage, because this should be able to monitor the state of charge, both the charge level, discharge level, and also the what is that, the heat loss, and okay, protection of the battery. All these things has to be taken care by this BMS, battery management system. This is integrated with the battery system, BMS. It comes with a separate model. Okay, what actually this BMS will do? Yes, this is this estimate, capacity estimate, like reaming capacity, full charge capacity, average current. That means even age, so that we can able to see aging compensation, self discharge compensation can be understood, and also the charging discharge current monitoring. What is the charging current, charging level, discharging level, and the present operation, that is the current status. So, and configurable for different capacities and voltages. So these are the some of the capabilities or the functionalities okay, of the battery management system. Okay, battery management system function, it comes with, okay, usually as the interface code system, it can be easily interfaced to a system with a LAN port or mounted display or RS-232 or nowadays even we have like, okay, that wireless interface via Bluetooth, Wi-Fi, and real-time data and estimation, self-calibration functionalities. So all of these are the things of this battery management system that is actually required. But however, the maintenance is also required. So maintenance, this battery management system also it takes care of the health of the battery system. That is a lifespan of, okay, of the battery system. That can able to identify unhealthy batteries, because when we do design the battery bank, we can do configure them in the both series and parallel configuration depending on the voltage and current levels which is required, because it need not be only single battery. So we can have a multiple batteries can be used, but which can be configured in both series and parallel as per the see the overall bank battery bank system is required. So in that case, even okay, your BMS can able to identify the unhealthy condition of the batteries, okay, so that it will be helpful to make a correction and easily debug and we can, okay, revert back. So and even okay, with IoT kind of things, we can also have a remote monitoring of see see your battery system in your vehicle or whatever. So on. So these are the some of the aspects of this battery management system, and other some in progress operation. Okay, that is the current status. In that case, over temperature in charging condition, over temperature in discharge condition, and whether unable to begin the charging. There are so many information and functionalities is possible with this battery management system. So we can do understand the BMS. It's not the battery just only alone. We are just connecting it to the power converter. But in between the power converter and the what is that battery system, we will have this battery management system. Also, yes, state of charge and state of discharge. All these things is able to monitor and maintain by battery management system in any battery integrated vehicle systems. And other okay, functionalities also, okay, it is average time to empty. That means how much time, how much average time is required to discharge your battery completely, and to charge your battery completely, what is the required average time. So everything, there are so many features, it comes with these battery management systems. Charge current, charge voltage rating, and state of health and battery configuration. So what configurations, the series parallel various configurations that we will have, all this. All these features can be in, okay, it comes with the battery management system, okay, which is very much required in the electric vehicle systems. Okay, so these are the this just only some information which I have taken from the website. So even the already in current various companies, they are working on these electric vehicles. So they do use these various types of batteries most of the vehicle systems they do use this lithium-ion batteries and their charge time. All these specs. Okay, anyway, this information is just I have taken just only from the website just to understand. Okay, anyway, there are other analytical things I can do discuss, but anyway, I already have taken a little more time.
Yes, sir. Yes, sir.
So I think I can stop here.
Okay, so we can take up some questions from participants, sir.
Yeah, if there is some questions, I'm happy to.
We request participants, if anybody have any clarifications or any questions, so please raise your hand. We can discuss with Narasimha sir. Sir, one question from Dr. R.S. Geeta.
Yeah.
Ma'am, can you please ask?
Hello, sir. Good morning.
Yeah,
So, first of all, thank you very much for exhaustive, insight about all the converters and the controllers for the different converters used in electric vehicle system. I just have one question on DC to DC converter. So, what actually is the type of DC to DC converter used in practice? Like there are so many DC to DC converters, interleaved converters are there, forward converters are there. So in practice, what is exactly used?
See, most of the topologies are basically derived from this basic conventional topologies, but otherwise now in the in applications, see, mostly in our say I talk about the vehicle system. Suppose in the charging systems, if you consider, see the normal converter, most of the converters are of like voltage fed converters.
Okay.
But otherwise, we do prefer this current fed converter. Now the current fed converters for the charging systems are in a very focus in that, because that current fed converters provides the constant. It doesn't lead to any pulsating current at the source side, and that way it can able to charge the systems, storage systems effectively.
Okay.
Yeah.
So is it better to go in for current controlled converters or voltage controlled converters? So
see, both are required. In fact, it is not that we can see. It all depends on our requirements. Suppose your application is such that only voltage regulation is sufficient, and we can go for voltage regulation. Otherwise, but in our charging systems, both are required.
Oh, thank you.
That's very important.
Sir, next question from Dr. Satish Chaudhary. Sir, so please, sir.
Good morning, sir.
Hello.
Good morning, sir.
Yeah, very good morning, please.
Sir, actually, the presentation was so nice and very informative one, sir. So I am also working on this field. So for my curiosity, I want to ask a question, sir. Whenever a battery is charged by a vehicle, suppose the vehicle is containing certain battery which is having some rating, some ampere rating. So how do you measure this consumption units?
Consumption means which consumption?
Suppose, sir, a battery is charged for 1 hour, suppose. So how we can calculate that energy consumption?
Oh, acha. So how much energy consumption is required for your vehicle? Okay, anyway, that depends on, suppose, see, what is your the requirements in your vehicle system and how long you need to run your vehicle. So it may be decided based on accordingly. But anyway,
that calculation I'm not asking. I'm asking, suppose a vehicle station is there, charging station is there, and that charging station is asking for some money for charging a battery for 1 hour or 2 hours, suppose. And how they are calculating that?
But I don't have much idea about that. But I know something about see, when we need to have a charge, see, when we need to charge our vehicle, so they'll okay. So even we have a fast charging and slow charging system.
That I understood. As
Yeah.
like in our household supply, we are consuming some amount of energy and we are paying for that, and some per unit cost is decided. So, sir, do you have any idea about the consumption of DC energy, that how they are paying the per unit cost? That was my question actually, sir.
Acha, acha. So I think I don't have much idea about that consumption.
Okay, sir. Actually, I'm not finding anywhere how they are charging and all. Though the calculation is very simple, that knowing the ampere hour of the battery and voltage rating, all energy can be calculated.
Yeah, yeah. It's a battery design part.
Yeah.
That's
Okay. Okay, sir. Thank you very much, sir.
Sir, next question from Ankush sir. So please, sir, please ask.
Hello.
hello.
Hello. Good morning, sir. I'm Ankush from Nagpur. Sir, my question is, can you please suggest some optimization technique for BMS?
No. Actually, this BMS information I just gone through, but I'm not exactly working on this BMS. So I don't know much about the design of a BMS, but I know what for actually the BMS is really good.
Okay. And sir, one more question is for energy management in electric vehicle, which parameter we consider considering electrical and mechanical point of view
Which
for energy management?
parameters in the sense actually the see the power management is nothing but okay. Management is something like okay, it is a coordination between your storage system and your propulsion system requirement and your energy source energy source. And okay, so this suppose now you say now you use the solar or fuel cell energy or IC engine energy. These are the energy sources in your vehicle.
Okay.
And also you will have a storage system on other side.
Okay.
And also you will have a propulsion system that is a load. Yes, see, your management is something like okay, and also you will have other auxiliary supplies, something like a audio system or lighting system, all these things. So your power converter maybe will be of multiple output voltage level converters. But which system is required at what time? And say, suppose now you don't want audio system or a lighting system. Okay, now one output will be say how to disable it, because you don't need to just simply operate that part. No, see.
Oh yes.
Is it not? Yeah, that part of auxiliary supply has to be enabled, right? Say, for example, only you are just operating your propulsion. That means you are only running the vehicle. You are not using any lighting and see this thing. And okay, then it need to provide the supply to the only the propulsion system rather than any other auxiliary things. Also, see whether your required power is taking from the actual sources directly or from this backup battery, right? So that also should understand. And that suppose you are even okay, suppose your propulsion system utilizes both the source energy as well as the backup storage energy, is it not? That means partial power power from the storage system as well as the partial power from the readily existing energy source. Okay.
Yeah.
So yeah, this way. So your energy management means it is something like this. Okay, it need to coordinate between the load source and the storage backup. All these things.
And sir, one more is considering regenerating braking scenario. Suppose we are using battery and supercapacitor. So which source is suitable for that regenerative braking scenario?
Regenerative means I couldn't get your question exactly. Supercapacitor and what is it?
Battery and supercapacitor, ultra capacitor.
Uses actually there are okay. I don't know very much about this ultra capacitors, all these cost effective. They're operating these things and all. But otherwise, I know that okay, but these are costly affairs as compared to this now the lithium batteries and all.
Yeah,
This,
yes.
yeah, they are much costlier and yeah. But I don't know much about.
Oh, we have a
Thank you,
session, sir. We have a session on super capacitors and ultra capacitors in tomorrow morning session. I think we can discuss more elaborately there.
At
Sir,
what time?
one question from our Dr. Dilip. How to decrease the battery charging time, sir? Normally, we have seen different batteries we can charge in different ways. How can reduce the time for battery charging?
Battery charging means suppose if you charge your battery system with a faster I current rating, then okay, your charging time is less only. It is fast charge.
Okay, okay, sir. Fast charging. So in mobiles also we are observing fast charging.
Yes.
Thank you, sir. Thank you very much, sir. We have get a very good idea about different grid systems and electric circuits. And you cover wide range of topics, sir, even high frequency converters, effective switching frequencies.
Yeah. Thank you.
DC to DC converters. Thank you, sir. Thank you very much, sir, for your kind acceptance.
I do not know how much mechanical people they have understood of these things, but
So even I am mechanical, I have some ideas, sir. Probably I am not able to understand the circuits because I studied long back. But the basic architecture, what you gone through, it is very easily understandable, sir. Thank you very much, sir. Thank you very much, sir.
But the thing is that today it's not just only mechanical and electrical to be isolated.
Yes, sir. Yes, sir. It is completely interdisciplinary team. We can work on everything.
Yes.
So, okay, sir. Okay, sir. Thank you, sir. Thank you very much, sir.
Yeah. Sir, welcome. Thanks. Thank you all.
Sir, small announcement for the participants. The next session from I think Mr. Deves Parekh, Manager, International Center for Automotive Technology. So his session will start in the afternoon at 2 o'clock. So I request all of you please join by 1:50 p.m. after lunch here, so we can start on time the second session. So please, sir, the second session link sent to you separately. So please see in that mail or WhatsApp. Afternoon session separately we sent a message. So please click that and we can able to join. So please, sir, we can start the second session at 2 o'clock. Thank you, sir. Thank you.
Sir, I see that.
Tell me, sir. Tell me, sir.
Yeah, the session on super capacitor at what time tomorrow?
Tomorrow morning 10 o'clock, sir, by Srinivasan Anandan from ARCA, sir, Hyderabad ARCA.
Oh, achha, okay.
Morning 10 o'clock, sir. Tomorrow.
Okay, I'll take pleasure to join.
Definitely, sir. Definitely. You are welcome, sir. You are welcome. Thank you,
Okay,
sir. Thank you, Anand. Thank you, sir. Thank you, sir.
Yeah. Thank you so much.
You can stop. You can close the sharing, sir.
Yeah. Thank you all. Thank you.